thank you for coming. I'm very happy to present this webinar today on microsecond resolved infrared spectroelectrochemistry. Our guest here in the webinar today is Professor Ian Burgess from the University of Saskatchewan, who's kindly agreed to present his research on this topic. So my name is Raphael Horvath. I'm an application engineer at IRSweep. My background is in infrared and Raman spectroscopy, and I've been with IRSweep for about 2.5 years now. My job is here to apply new applications to the spectrometer that we sell and produce, the IRIS-F1. But I haven't had anything to do with the work that Ian will be presenting today, so I'm very excited to hear about it as well. I think it's fair to say that Ian has been interested in surface chemistry for most of his academic career. He started at the University of Guelph, where he studied biomimetic layers and surfactant assembly. He then did a postdoc at McGill, where he worked on monolayer self-assembly and the electrochemistry of nanoparticles. In 2005, Ian joined the Department of Chemistry at the University of Saskatchewan, where he is now a professor. He's still interested in surface chemistry and electrochemistry, but also now in surface-enhanced spectroscopy, which will be a major part of the talk today. So the agenda for the talk is shown here. So I've just done the introduction. I will first start by talking a little bit about dual-comb spectroscopy and how we implemented that in the IRSweep spectrometer. This is just so people get we're all on the same page of what the rest of the talk will be about. And then Ian will give sort of the main presentation about the work that they did on the infrared spectroelectrochemistry. At the end, there will be a Q&A session. So if you have any questions, there should be a Q&A tab where you can ask questions throughout the talk, and I will read them out in chronological order after the talk, and we will go through them and discuss them. So as you probably know, IRSweep heavily relies on frequency combs. So we produce a spectrometer in the mid-infrared, which is based on dual-comb spectroscopy. And the frequency comb, sort of the underlying technology of this is essentially an optical source which consists of many equidistant modes, and that's sort of depicted in this equation. Where f0 is an offset, and then you have n number of modes which are spaced with this parameter frep. And frep is the distance between the comb lines. For us, what's very important about it is that it's a broadband source. It has very stable interline spacing, so frep is very stable. It has many narrow lines, and it is quite powerful because it's a laser. As you can see quite nicely from this from the depiction in the middle, frequency combs are used for many different applications, ranging from optical clocks to waveform generation and coherent LiDAR. And each application has sort of its own set of parameters that it requires, and sets of how precise it has to be, how broad it has to be, and so on. So there are also many different ways of generating frequency combs. For us, we're sort of in the middle in terms of the requirements. We do molecular spectroscopy, and the source that we've chosen for this is quantum cascade lasers. And the reasons sort of listed here, we chose quantum cascade lasers because they're bright. They give several hundred milliwatts of optical power if you want to. They're very robust, meaning that you can engineer them into a system that is essentially turnkey. It turns on and it runs. There's no It's a monolithic system that's completely integrated into the chip in principle. It has quite low power requirements, and you can get quite high time resolutions, which I'll mention later. A typical spectrum is shown on the left here. So this is about 80 wave numbers broad here. 60 to 80 wave numbers is typical for a QCL comb. I should mention on the point of compactness, this is the picture there shows the submount of such a laser, and the actual laser chip is the small small bar in the middle. So the laser itself is actually really, really small. And so it's definitely a scalable technology as well. To do spectroscopy with frequency combs, you need two of them, or at least the implementation that we have, you need two of them. You overlay them on a beam splitter, meaning that the beams are collinear. Then you pass them through a sample and use a single pixel detector to deconvolute the spectrum. And that's sort of the trick. The reason you need frequency combs is this deconvolution step. The way it works is depicted at the bottom. So you have these two combs depicted in green and in black, comb 1 and comb 2. And each of them have almost the same f-rep, so the same spacing, but not exactly the same. And it's the difference in this comb spacing that's sort of the key for the spectroscopy, because when you overlay them, you get a heterodyne beating in the radio frequency domain. It's in the radio frequency domain because we can choose the f-reps to be almost the same. So the difference is usually on the order of 1 to 5 megahertz. So you essentially get a mirroring of the optical domain into the radio frequency domain, and when you measure that, you can measure it in the time domain. It's a ringing. You can do a Fourier transform and get back the spectrum that you started with. Here's another way of looking at this. So at the top is the two optical spectra of the two combs. In red and gray are the two different lasers. And the resulting radio frequency spectrum is shown in the bottom. So it's the difference between the neighboring lines that produces the actual beating. And because the difference increases incrementally, because the spacing is extremely stable, the radio frequency spectrum also increases incrementally in the same way. If you introduce an absorber into this, then the absorption of the optical spectrum is also seen in the radio frequency spectrum. So that this is how we can measure something in the radio frequency spectrum that actually happens in the optical domain. So that's the equation here that I've sort of described here, where delta f-rep is one f-rep minus the other. And the time resolution is giving us the inverse of the f-rep. And this means that you need a larger f-rep to get a better time resolution. And in our case, this is on the order of 1 microsecond. And also, there are no moving parts. I mean, this is Fourier transform spectroscopy, essentially, where each arm of the interferometer is replaced with an individual laser. So it's quite a robust solution. What that gives you in terms of specifications, so these are the current specifications for the instrument that we sell. I guess the standout is the time resolution of 1 microsecond. You have that at full spectral resolution or spectral point spacing, which is about 1/3 of a wave number. This is laser dependent. What is also laser dependent is the bandwidth, but it's typically between 60 and 80 wave numbers. And the laser power is usually about 50 milliwatts in the sample compartment. People don't really care so much about the power, they care more about the signal to noise. So that's what we're depicting here in the figure. What this figure shows is the standard deviation of a measurement line. So in other words, a measure of the noise, and how it changes with integration time. So on the x-axis is integration time, and as you expect with longer integration time, the standard deviation drops. So this is a square root relationship, which is very common in spectroscopy. We compare this to an FTIR, where we use a liquid nitrogen cooled MCT detector for the FTIR. We try to be as fair as possible. And the level of noise is about 100 times bigger in the FTIR. This is not very surprising. An FTIR is relying on a glow bar source, whereas we have a laser. So for these short time scales, you do get much better signal to noise compared to traditional spectroscopic techniques. So this is in the backdrop, and this is the instrument that we sell. Ian is one of the users of the instrument, and I will give over to him so he can show us what they've done with it.
Okay, thanks, Rafael. Does everybody see this on the screen?
It's good.
Okay, excellent. Okay, so I'm going to talk a little bit about our use of the IR sweep instrument to do infrared spectroelectrochemistry. And I'm going to begin with an introduction to the technique that we use, which is attenuated total reflection surface enhanced infrared absorption spectroscopy. So ATR SEIRAS, which is the abbreviation for the full title, basically works in a Kretschmann type configuration, where you take a standard internal reflection element, such as a silicon hemisphere or a zinc selenide prism, and you work with incident light that comes in above the critical angle so that you can couple an evanescent wave. But unlike a regular ATR experiment, you put a film of conductive metal on top of the principal reflecting plane of your internal reflection element so that the evanescent wave actually couples in with the free electrons in the conductive layer. And this is hugely advantageous for spectroelectrochemistry because that metal layer can serve as your working electrode in an electrochemical environment. And because now you're talking about really light which is confined to the length scales below that of the evanescent wave, you no longer have to worry about bringing your infrared light in an external reflection geometry through a highly absorbing medium of water. So the gold film or the metal film that you put on top of the internal reflection element becomes key. So it's usually modeled as a collection of gold islands. And this is important because the optical properties of this sort of collection of gold islands, which could be near the percolation threshold or below the percolation threshold, is quite different from the equivalent optical properties of a continuous film of say, gold in this example. So this is hugely important. If you try and do the experiment with an atomically flat layer of gold on top of the internal reflection element, you don't actually get any SEIRAS surface enhancement. So you can model the optical properties of your metallized film in a variety of approaches. The one that we like is effective medium theories. So this is basically taken from Osawa's work from the early 90s. Osawa was sort of the guru of infrared spectroelectrochemistry using ATR SEIRAS. And what you can do is you can take these collections of prolate ellipsoids and you can model an effective medium for them in terms of the bare metal nanoparticle, but then also when the metal particle is coated with a layer of molecules which are modeled as a simple Lorentz oscillator. And to make a long story somewhat oversimplified and shorter, what you can see is you get massive enhancements in the apparent absorbance of a thin layer when you have these collections of metal particles on the surface. So the graph on the bottom left is basically showing you an absorbance measurement for a Lorentz oscillator with a peak frequency of 1300 wave numbers. That's the red line using p-polarized light. And then in yellow, you can see the equivalent absorbance that you would get in an external reflection experiment with a monolayer absorbed on a continuous gold film. And so you can see there's a massive increase in the apparent absorbance. And this enhancement factor is highly angle dependent. The graph on the right-hand side is basically just showing that dependence. And you can see you have a peak at relatively grazing angles, although that depends somewhat on the precise structure of the metal nanoparticle film. So if you've kind of missed any of that, you can kind of think of ATR SEIRAS as just the infrared equivalent of surface enhanced Raman spectroscopy, with one important caveat. SERS tends to be dominated, or the enhancement factor in SERS tends to be very strong for coinage metals, gold and silver particularly. When you try and do SERS on a film such as palladium or platinum, which are highly important for electrocatalysis processes, usually your SERS signals is very much weaker, much, maybe a 1,000-fold smaller enhancements. Whereas for SEIRAS, the nature of that metal film plays a much smaller role in the overall enhancement factors. In the bottom panels here, I'm showing the so-called G factor. That's just an empirical measurement of the SEIRAS level of absorbance compared to an external reflection absorbance for a continuous film made of that metal. So you get G factors of about 10 to 20 for platinum, gold, and copper. And in fact, you can go through the 3D block of transition metals and you can find papers where very strong ATR SEIRAS enhancements have been reported, and they've been used for electrochemical ATR SEIRAS. Right. Okay. So now I'm going to just talk a little bit about why you would want to have very high time resolution spectroelectrochemistry using infrared light. And so this is some work from Ataka and Eberle from early 2000s, where you take a redox active protein such as cytochrome C, and you attach it to a gold electrode surface, which is modified by a self-assembled monolayer. And you can modify the thickness of that self-assembled monolayer, so you can just change the number of methylene units. And then what you can do is you can toggle the oxidation state of that heme center by applying different potentials. And along with the electron transfer process, there's actually a configurational change in the protein. And so, it's kind of interesting to ask the question, well, what comes first? Does the protein adopt a different conformation and then the electron transfer occurs, or is it vice versa? So just to give you an idea that you can follow that with infrared spectroelectrochemistry, you can follow the amide 1 bands, and you can see changes in those amide 1 structures as a function of potential. And to answer this question about, what's going on in terms of the dynamics of the molecule, you can adopt the two-state gated electron transfer model, where the observed rate constant is really just the sum of either the reorientation kinetics or the electron transfer kinetics. And so you can plot this natural log of the apparent rate constant as a function of the number of methylene units in the spacer layer. And what you can see is if your spacer layer is quite large, then your apparent rate constant is dominated by or is controlled by the electron transfer process. That's the rate determining step. And you get the exponential dependence on the thickness of the SEM, as you might expect. But below sort of a critical value of methylene units of maybe 8, you can see now the kinetics are controlled by the reorientation, and they all plateau. And you can take the sort of asymptote at a low number of methylene units to come up with a rough idea of the magnitude of the reorientation rate constant. And you can see it's on the order of about 10 to the 5 inverse seconds. So that just kind of gives you a back of the envelope calculation that if you wanted to study just the kinetics of the reorientation process, you're going to need time-resolved infrared spectroscopy with 10 microsecond or better resolution. And so for a number of years, my group has been trying to pursue the idea of doing microsecond level time resolution in spectroelectrochemistry. So there's some obvious challenges associated with doing spectroelectrochemistry on that level of time scale. One of the big problems is the so-called electrochemical time constant, which is just the product of your electrolyte solution's resistance times the capacitance of the interface that you're trying to study. The capacitance scales with the area of your interface. So if you want to work with microsecond level timescales, you need to have an electrode area which is very, very small. And this is hugely problematic if you want to use external reflection techniques and conventional sources, simply because you're starved for photon optical throughput, that you tend to need to have a large electrode. And if you're working in external reflection mode, the attenuation of the infrared light by the solvent is just way too problematic. So what you really need are bright sources. And so the bright sources that we've worked with for a number of years have been principally the synchrotron. We're very fortunate that our university also is home to Canada's synchrotron, the Canadian light source. And so we've been using the mid-infrared beamlines at the Canadian light source to do a lot of experiments over the last 10 years or so. And then lately, lasers. So the advantage of the lasers, Raphael kind of described in the beginning to this talk. But we'll just give you an example here of why the other methodology limitation is the nature of interferometry. So if you want to do microsecond level experiments with a conventional instrument, you have to do step scan interferometry. And here's a result in the purple trace of a very simple redox active system, which is also infrared active. This is ferrocyanide. And we just measured this transient absorption after stepping the potential and changing the redox state of the ferrocyanide. This was done with an ultramicro electrode, an external reflection technique at the Canadian light source. And you can see it's quite a noisy final trace, and that's the result of 256 co-added spectra. But in order to do step scan, it takes about 10 minutes to collect a single spectrum. So that entire experiment took a total of 1.8 days. And of course, that just eats up an inordinate amount of beam time, and it's just not a feasible way of doing these types of measurements. And we realized then when we heard about the about the IR sweep instrument, that this would be an excellent potential application. This would really solve this problem of very long experimental times, which paradoxically are required to do high resolution time experiments. So we were very fortunate in late 2018, we had a grant accepted and we were able to purchase the IR sweep, IRIS F1, and it was installed in late 2018. The system that is now in use is got a 6 micron QCL, and that gives us a bandwidth of about plus or minus 40 wave numbers. And this instrument was purchased in collaboration with the Canadian Light Source, the mid-infrared beamline, and is now currently installed at the Canadian Light Source. And it is accessible on a user access basis if you write an application. And at the end of the talk, I'll give a little link and instructions on how you might go about doing that if you're interested. So this is a picture of one of our earlier system setups to do the spectroelectrochemistry experiments. This young man is Eric Linz. He's the PhD student who did all of this work. And the experiment configuration consists of a commercially available external reflection accessory and spectroelectrochemical cell, both of which are commercially available from Pike Technologies. And you simply mount this in the main optical chamber of the IR sweep instrument in the same way that you would with a regular IR bench, such as a Brooker instrument. Turned out that it was a little bit more challenging than that. We had to reconfigure the optics quite a bit in the external reflection accessory. The Pike boxes expect incident light, which is converging light, and of course the lasers are collimated. So we had to sort of readjust and modify some of the mirrors. And so this is just a picture on the bottom of the laser table that we set up. And the green and red dots basically show the process of trying to make sure that the beam is completely symmetric through the external reflection accessory. And this took us a little while to make sure that we had the optics configured correctly. We also found out that using the laser system, that the focus was much tighter than we were used to with a conventional source. And this meant that our latest generation of the experiment requires the 3-axis positioner to hold the spectroelectrochemical cell, because the throughput is just incredibly sensitive to the exact position of where your sample is. So once we worked through a couple of those bugs, we were ready to go, and we were able to do some spectroelectrochemistry. So the system that we decided to study was a very simple system. It's the adsorption and desorption of a soluble pyridine derivative, dimethylaminopyridine. And we've been interested in dimethylaminopyridine because it's a stabilizer for gold nanoparticles. And so we were very interested in studying its absorption. And we'd published on this system 10 years ago or so. The spectrum, a series of spectra that I'm showing in the main graph, those basically show the potential dependent absorption of DMAP, dimethylaminopyridine. And the nice thing is the blue sort of box there highlights the bandwidth that were accessible with the IR sweep QCL combs. And there's a very strong absorption from the DMAP molecule at about 1620 wave numbers. So to do the experiment, we took a 25 millimeter diameter silicon prism, and then we deposited a thin layer of indium tin oxide, upon which we can electrodeposit the gold layer, which has that right texturing to give you the SEIRAS enhancement. And that methodology is described in a 2019 paper. We didn't make any effort to make the electrode area small for these initial experiments, so it's still quite large. The electrode area is about 0.3 square centimeters, and that will come back and be important with some of the results that I show you in a minute. So the experiment was pretty simple. The top left graph is showing you the potential step sequence. So we basically hold at a potential 300 millivolts versus silver chloride, where the DMAP molecule absorbs on the gold surface in the form of a monolayer. It's got a surface coverage of about 7 times 10 to the minus 10 moles per square centimeter. And then we step the potential to negative potentials, minus 900 millivolts, and the DMAP completely desorbs from the gold. The black line in that trace is basically the idealized experiment where the potential is manifest at the interface instantaneously. But because of the finite resistance of the cell and the capacitance of the interface, the time constant was actually about 20 milliseconds. So the red trace actually shows you the real manifestation of the potential when you do the experiment. And we just repeated that experiment where after about 15 seconds, the potential is adjusted. And we measure then time-resolved spectra for the desorption of the DMAP molecule. And we repeated that loop 128 times. And the bottom right shows you a heat map of the change in the absorbance as a function of time. So you can see there's a very pronounced peak, which grows. Actually, it's a negative going peak because we're doing a desorption experiment at about 1627 wave numbers. And then there are 3 spectra that are just taken at 3 intervals, 0 milliseconds, 15 milliseconds, 20 milliseconds, just so you can get an idea of the signal to noise levels that are being acquired. Those spectra were computed using 20 microsecond time binning and a spectral resolution of 3.3 wave numbers. And the key thing here is this entire experiment took 30 minutes as compared to an analogous step scan experiment that we did 10 years earlier on a different system, which took almost 2 days. So that really illustrates, in my mind, the primary advantage of the IR sweep technology. Just to give you some idea, there are some transients. So these are just the peak area for that DMAP peak, integrated and then plotted as a function of time with either 20 microsecond time binning or 200 microsecond time binning. The nice thing about the information that you record is you can post-process it to your heart's delight. And then the red line is the empirical fit just to a double exponential. And you can see that there are actually 2 time constants for the observed transient. One which is very quick, well, relatively quick, 1.5 milliseconds, and the other one's closer to 40 milliseconds. And just to give you an idea of how fast the event is expected to be, you can make a crude estimation of the time that it would take for a monolayer to diffuse a distance of about 5 nanometers from the surface. Once your molecule is at a distance of 5 nanometers or greater from the surface, the SEIRAS enhancement is essentially negligible, and so you should have no signal. And so you can see that that estimated time scale is about 1 microsecond. So clearly, our measured transient is much, much slower than the expected response. And this basically comes down to the fact that we're not working with an ultramicro electrode yet. And what we're really measuring is the rise time of the potential step. So our next steps and what we're going to do as soon as we're allowed back into the facility and are able to continue experiments is to repeat these types of measurements using true ultramicro electrodes and really be able to access the microsecond time scale. But the data gives us an excellent opportunity to sort of quantify how good the measurements could be. So we can either make these Allen plots that Raphael described at the beginning, either by changing the time binning level, that's delta T, or we can adjust the number of co-added spectra. And in both cases with these noise plots, you can see that the noise scales with an inverse square root relationship, as you would expect. And then you can do a back of the envelope calculation. So a monolayer of DMAP, which is a moderately strong adsorber, provides a signal of about 11 milliabsorbance. And so if you wanted to say, well, look, I'm going to need a signal to noise level of about 3 or greater, and I want to be able to measure 5% of a monolayer, that gives you a noise floor expectation of about 0.2 milliabsorbance units. So if you just add these sort of red horizontal lines at that noise level, 0.2 milliabsorbance, you can begin to see where your threshold is for your time resolution experiments. And if I just draw everybody's attention to the blue trace, that's with 128 co-added spectra, you can see that we can get to 10 microsecond resolution and reach that noise requirement pretty handily. And that was 128 scans took about 30 minutes. So we could easily increase that by a factor of 4, decrease the noise by a further factor of 2, and it would only take us, what, 2 hours. So I'll just conclude there. So this is the first demonstration of electrochemical ATR SEIRAS with the dual comb technique and the IR sweep instrument. The key take-home message, I think, is that the experiment required 2 orders of magnitude less real-time compared to a step scan interferometry experiment. We've demonstrated that you can measure sub-monolayer concentrations down to about 5% of a monolayer with 10 microsecond resolution. And the good news is we've been in collaboration with Pike Technologies, and those modifications that we made to the external reflection accessory are now commercially available, and Pike is selling now systems that are ready to go for laser-based instruments. And the spectroelectrochemical cell is also available through Pike Technologies. So my last little remarks here is I'd like to acknowledge the Canadian Light Source Mid-Infrared Beamline team. So this is Drs. Scott Rosendahl and Stuart Reed. They were instrumental in getting this thing up and running. And now that the instrument is commissioned, the Beamline is accepting proposals for use of the IR sweep instrument. And that doesn't necessarily mean only spectroelectrochemistry. If you have other applications that you'd like to try, I would suggest you contact Scott at that email address, and he can sort of guide you through the proposal writing process. And so with that, I'd like to thank everybody for their attention, and I'll turn it back over to Raphael.
Great, thanks very much. I will go back to my screen. So if you have any questions, please post them. I will quickly start. The Beamline applications, are they open to Canadians only, or is it international?
International.
Okay. Right, so then, where are the questions? Okay, we'll just stop this. Okay, so questions. The first question, do you know what each of the 2 timescales is due to?
It's an interesting question. At least one of them is just the RC time constant. I think that's the higher time constant that was about 40 milliseconds or so. That's comparable to what we measured with electrochemical impedance. The other one is more interesting, and I'm not 100% sure, but I think it's something to do with the conductive metal oxide layer, the indium tin oxide. If you look carefully at that heat map that I showed, you can see that the baseline level is also changing. There's a non-zero absorption off resonance from the peak. And we think that's something to do with charge injection into the conductive metal oxide, which is, you know, a highly doped semiconductor. But that's all very speculative at this point.
Mm-hmm. So another question is, could you track mechanisms, for example, CO2 electrochemical reductions on a silver or gold surface using this type of measurement?
Yeah, I think so. I think if you're looking for any sort of transient species in small molecule electrocatalysis, this would be an ideal way to go. CO2, ammonia production from nitrogen reduction, methanol oxidation, any of these sort of electrocatalytically active or interesting systems. If you're looking for the dynamics in transient adsorbed species, this would be the ideal methodology for sure.
Mm-hmm. Another question is, how would you go forward to get shorter RC time constants?
Yeah, the obvious one is just to increase the ionic strength of the electrolyte. I don't think I mentioned it out loud, but the electrolyte was only 50 millimolar sodium fluoride. But if you went to something like 0.5 molar potassium chloride, your resistance of your electrolyte would go down by about an order of magnitude, and there would be a commensurate decrease in your RC time constant. But the big thing, of course, is to decrease the electrode area. If you want to get to microseconds, we've got to do some sort of lithography to print ultramicro electrodes onto the crystals. It's a bit of a challenge with those larger prisms to do the lithography, but there's alternate ways that you can do this with wafer-based internal reflection elements.
Mm-hmm. So then there's a question that asks about the IRIS-F1 instrument. It says, what are the main reasons why this technology is so much faster than StepScan FTIR? And can it be used to study non-reproducible reactions where StepScan FTIR is not applicable? I think I'll answer this one. So one of the reasons is brightness. So you have a far larger number of photons, so you get a better signal to noise. But also there are no moving parts, so you're not reliant on a mirror moving. This is of course only relative to rapid scan, where you move the mirror very fast. But in step scan you still have to move the mirror, and therefore you have to take many acquisitions to get through this. So yes, this is a way to get around the non-reproducibility issue that you can't get around with step scan, where you have to really repeat the experiment many hundreds of times or thousands of times to get a full data set. And you can actually do single shot reactions. I think the last webinar about combustion showed that quite nicely, because in these combustion events you could only take single shot measurements. Another question, which I think is a follow-up to your previous answer, is why do you use ITO? Can you use other semi-transparent metals or metal oxides as adhesive layers?
Yes, you can, kind of. So typically, if you're trying to put gold onto a silicon surface, you have lots of problems with delamination. And the way the electrochemistry community and others have addressed that in the past is to use chromium or titanium buffer layers. And there's one report in the literature where titanium was used as an adhesive layer for the gold. And we tried this and we never got strong enhancement at all. It was hugely problematic. And we think it's basically that the titanium provides a very smooth layer of gold, which gives you very weak enhancement. So the indium tin oxide is quite nice, because it is quite transparent. If you don't dope it too much, if you keep the doping level relatively low, then your plasma frequency for the ITO is about 4,000 wave numbers, if I remember correctly. And that works beautifully. It's conductive enough that you can do these experiments, but it doesn't have such a carrier density that it absorbs in the infrared. Not until you get up to sort of far infrared does that start to become problematic. So the short answer there is, yeah, these traditional buffer layers of titanium and chromium are just very problematic, at least in our hands, in terms of getting seras enhancement. And you really want the gold either to be on a truly transparent material, such as the conductive metal oxides, or better yet is to have the gold directly on the silicon. The gold directly on the silicon gives you nice enhancement, but it's incredibly fragile. Every time you try and take the cell apart, you'll lose your gold film. And the indium tin oxide works beautifully as this buffer layer. Once you deposit the gold on there, you can take the cell apart, you can do various chemistry and reassemble, and your gold is robust.
And another question just came in. What is the beam size of the IR source? It's about 3 millimeters, but it's quite straightforward to expand or focus. I guess in your system it's smaller when it actually hits the crystal. Is that correct?
Yeah, I'm trying to remember what the demagnification factor would be in the Pike box. I think it's about, if I remember correctly, it's about 1 millimeter at focus. Yeah, ignoring any. Yeah, if you don't have any of the silicon prism on there, if you just look at the beam spot on the external reflection accessory, it's about 1 millimeter in diameter.
Mm-hmm. Cool. Well, for now that answers all of the questions. I just would like to quickly advertise the upcoming webinars. So we're trying to make a full series so people can still see talks even in this period of no conferences. The next one is about high resolution and gapless dual comb spectroscopy with current tuned quantum cascade lasers. So it's filling in the gaps between the lines. And it's on the 25th of June. But there are more upcoming, so if you're interested, please check our website, and yeah, there will be more stuff posted. Actually, I have one more question that I thought of. I've recently come across excitation modulation spectroscopy, where you apply, say, a square wave electric field or something to modulate the sample to enhance the signal. Is it something that you could incorporate with your experiment?
Yes, I think you could. This is the equivalent to photoelastic modulation infrared absorption spectroscopy. We have a double modulation. You can either do that with the PEM, or you can do this by modulating the potential as the question asks. Usually you do this if you're trying to increase your signal to noise further, and not necessarily do time resolved measurements. So you could definitely do that. I think the data that we have in hand is just super encouraging, that the signal to noise is already very, very high. And so the gain by actually doing those double modulation experiments would, increase your signal to noise by a commensurate amount, but it may not be needed if the signal to noise is already suitably high. But if you had like a really weak absorber, for example, and you're looking for that, then yeah, you could definitely do this. I have to think a little bit about how you would actually do the data data acquisition and actually the measurement, because you would need either a demodulator or a lock-in amplifier. But as long as you can take the signal out of the detectors, then yeah, I think you could do this experiment.
Okay. Great, and I think that concludes all the questions. So thanks again, everybody, for coming. Thank you, Ian, for the very nice presentation.
My pleasure.
And yeah, if you have any questions, please get in touch with myself or with Ian. And if you want to go back and rewatch parts of the webinar that you missed, it will be up on our website as well. So thanks and goodbye.